Hello, Professor.
Okay, hello, Sarah.
Hello, Professor.
Hello,
How are you?
Boston. And hello, Kay, once again. I see you're connected twice.
Two accounts.
Sarah, did you figure out the way to graphically connect?
No, unfortunately,
And please try to speak something. Maybe I need to do the stuff that Boston taught me. Just a second. Okay, please try to speak now.
I have tried the suggestion that you sent me through the email last week, but unfortunately they didn't work, and still my laptop has problem.
Okay, you. Well, I'll try to look on it maybe this night once again and share what I see. Do you have the Windows computer near you? No?
No, I have Mac.
Okay. If by the next week we do not solve, maybe you might try to come to the lab or have access to Windows computer at home, because there it is not needed for the whole semester. It's maybe just one or two labs when you will process graphical information that has to be done on the Gaussian. And there are alternative ways I will show what and how to do, but they are less efficient. They will take time and effort. So in Gaussian through graphical tunneling, it's much easier and better. So what are we going to do? So we have finished the chapter 1 on the geometry optimization, and from now on we are coming to chapter 2, the studies covering on lecture on Friday, so-called hard-to-focus method, which is the simplest or maybe most logical method to compute organic structure. If you do remember from what we did in class, if one needs to deal with G-order optimization, if one needs to browse through potential surfaces, there should be Coulombic function times plus eigenstate of the ground electronic state most of the times, and sometimes accelerated electronic state. So the question, and you remember we did separate molecular physical equation onto linear part and electronic part. So as you see, in order to browse along potential energy surface, we need to know solution of electronic part for each intermolecular distance. So for this problem, one can forget about moving of ions, assume that someone just nailed them to the space, and we are looking only on the electrons. And based on the all possible, so based on the solution of this so-called electronic structure problem, we will find eigenstate of all electrons, or energy of ground state of all electrons, and this energy will be forwarded to the potential energy surface if we need to find important distances. Some people consider this problem of finding total energy for electrons which move in the attractive field of multiple ions as computational chemistry in a narrow sense. So I do not support this splitting, but some people consider that anything that deals with atomic dynamics is like molecular dynamics and molecular mechanics, and actual computational chemistry is only electronics. No, I do not think so, but some people believe in that. And right now it's not a lecture, I will not show equations, but we need to practically find how to get the energy for the ground state of the system. So you already know how to draw molecule in Gaussian, and then now we need to learn how to find how to throw in electrons and find where they are. And for maybe 3 labs, we will focus only on so-called hard methods. It's not the best for practical applications. It's a little strange if you do it for any scientific problems and publications, but educationally we need to include it because it is maybe the best in terms of explaining logically how it works, how which equations are behind this. And it has much less cheesy approximation than other methods. One thing and another is relatively quick. So what I do have plan minimum and plan maximum. So plan minimum is to draw an example simple molecule, find which mouse buttons are needed for the Gaussian application to run everything in such calculation, and extract total energy. I promise that we will get to this point, and you see the motivation for this, because this total energy later can be used to construct potential energy sources. Okay? Although we are not going to go to potential energy sources right now, but you understand why it is. Time maximum is to inspect the output file of the Gaussian in the text format, find where this information about total energy is placed there, and then we will need to start learning the concept of molecular orbitals. For it is quite natural concept that you already know intuitively, especially in organic chemistry, and everyone knows atomic orbitals for hydrogen. And in the lectures, we will go through rigorous definitions, and now we need just to see these molecular orbitals, how electrons are distributed in space, in the form of colorful figures, like the balloons around the world. On the other hand, the orbitals have different energies, and we need to discuss what do these energies mean and how do they relate to the ground state total energy of all electrons in the system. Any questions to this motivation part? Now I invite everyone to look into the photon server and open those here, and let me know when we're done with it. Let me know if you can. So to start, I already have it. I'll start sharing screen soon. For Sarah, if graphical connection is not working, I will make some immediate suggestions for you. So while everyone else is opening those views, I will try to show something. Yeah, Boston, I see your message. Thank you. So, I'm talking right now primarily to Sarah, but as everyone is ready, this goes for you. Please tell me by voice or by chat line, and I'll start demonstration for everyone. So, Sarah, you still need to log in and look at your directory, right? So I did share the file that everyone else will create manually by graphical design. And this file, later I will need to explain it to everyone. So in some sense, you are ahead of the class. So we will create graphically the input file that connects the Cartesian coordinates. And in addition, there is a line for keywords. So the most important keyword here is HF for Hartree-Fock. And as soon as this file is ready, one can run the Gaussian by this command G09, and then the name of the input file that ends with .com. So here it works really quick, but in most practical problems it will work for hours or days. And upon it is done, there is a file which is named .log. So which if you type, we will do it together with class, but if one looks for grep, it will give this energy of Hartree-Fock minus something atomic units. So this total energy is the goal of our program minimum. So while we are talking to the rest of the class, please log into your directory and explore these files. In order to do it, one can create the files manually or copy or download it or upload it from the local computer. But most important thing is to run and see how it works. Does it make sense? Sarah, please ask questions if needed. And you're muted now.
Yeah, unfortunately I'm not able to connect to the.
What do you mean? You cannot do SSH?
Yeah.
It looks a little strange because if you can transmit voice and image, it means the internet works well. Can you let me make everyone?
I'm not able to go to Scratch directory.
Oh, so you already logged in, but you cannot find. You should be able. I think it is just a little technical issue that you'll solve in a second. Let me share. Share this line in the chat.
I think Kia, you should make directory for lab4. I think.
Yes, but for in your directory, I already did it.
Okay.
I just went to your subdirectory and opened. For everyone else, just wait until I give instructions.
Okay.
They were what I was showing. It was personal. Make sense?
Okay.
So, any quick questions from Sarah?
It says that there isn't any directory for Scratch 001. I don't know why. I'm in the photo now.
Are you logged under name queuing, or you made your another user you got special username for yourself?
No,
just type the. Oh, I'm sending it to Boston. I should send it to everyone. Just please type this command that I sent to everyone, or copy paste it.
Okay. Okay, it's worked.
Okay, so just look through these files and let me share the commands. So this one is for paste. Just a second. Job submission.
Yeah, now it's worked.
Good. But please, the rest of the class, please do not go to the directory of Sarah, right? You should do things in your own directories.
Yes. Okay.
So, copy, paste.
Okay.
And just right now, for about 30 minutes or more, we will be doing graphical information, but everyone will come to the same stage.
Okay.
Okay.
Thank you.
Well, did you log in? Dina? Okay. So I do not request, but suggest that you create specific directory for each individual lab, and later on, when we will be doing more calculations, I would suggest that we create new directory for each specific calculation. Otherwise, it will be a big mess, not possible to go through. So now, in the Gaussian, I suggest that you just create new model, and I suggest a specific molecule which is kind of partially inorganic, partially organic, partially it is semiconductor, but very small. So it is a molecule that shares properties of several classes of materials. So it is titanium hydroxide. So I'm going into elements, right? Titanium hydroxide, which means, so let's find titanium. So it's third row transition metals. I'm clicking on titanium, and I select the tetrahedron. If feel free to ask questions. if you are in organic, just in any chemistry, it's natural work, tetrahedral. If you are in other disciplines, so tetra means 4, so it's like a center is 4 legs. I select this titanium tetrahedral, click in the molecule, right? And now I need to create to put oxygen, so I find oxygen and click on each of these 4 legs. 1, 2, 3, 4. So molecule is done. What is the reason? So the preferred oxidation state of titanium is 4+. When 4 electrons are removed, and hydroxyl group is electron withdrawing group. So each hydroxyl takes 1 electron from outside. In total, it will be neutral, but each part of this little molecule will be happy for charge balance. So
create hydrogen atom plates.
So I'll walk through the class and ask those who need help to share screen. So please come to the stage so that everyone has this moment. So before we go to electronic structure, we need to optimize it, and we can click onto the broomstick, and after that you see it slightly changed, and then we can do quickly the optimization in the Gaussian form. So it is important step for any practical calculations, but I will spend only 1 minute for it. So just watch carefully, because it is very small part in the, we already passed it in the lecture material. So save the molecule, save, and then create some name. So it's better if you create a name that is self-explanatory. Like titanium 04H4 by hand, right? For example. Now look in the menu number 4, Gaussian calculation setup. So click there, and in the Gaussian calculation setup, there is a menu. First, job type, you need to select optimization, because we need to optimize. In method, right now, we need to choose mechanical, because it is the quickest. Mechanical means for universal force field.
Oh, sorry, it's similar like Avogadro, because I'm able to.
No. Please do in Gauss U. If you are not able to connect to Gauss U, then do the same as Sarah is doing and talk to her. The procedure that I'm showing right now will be not available in Avogadro.
Okay.
So you need to in the second menu you need to select mechanics and UFF, universal force field, and then you click submit, and it asks for save. So you must save Gaussian input file before you submit. Would you like to save an input file right now? You save. You can add the name like optimize universal force field, and save, and submit the following file to Gaussian. Okay. and a few seconds later it is done. So you need to select this the .log file that ends with the log extension.
So what's the file type? Because you can.
So I will answer your question in a second. And, I will not go forward until everyone's at the same stage.
But
Just wait, I need to give comment to everyone. There could be a little deceptive impression that Gauss view does many things itself. It does not. Gauss view here on this photon server is naturally connected to Gaussian program. Those are two different pieces of software. They're done by the same company. They often are sold together, but they are different pieces. And most data centers buy only Gaussian, do not buy Gaussian to save money. So what we are doing right now is a only educational procedure that makes it a pleasant experience. But for productive computation, later on we will do everything in text, in command line, without any graphical content. So what I did show right now was skipping any command line because the system administrator established natural piping, natural transfer of data from Gauss view to Gaussian and then back. So if you have problems with graphical connection, you still will be able to run Gaussian. You don't need any graphical information. But for this transferring, we need to work in the graphical form, so-called X forwarding. Let me walk through the sheets and ask everyone if everyone has this molecule, and then I will with you for a question in a second. Okay, huh? Did you run optimization yet? We did something other than you see this low energy ticker comes from electronic structure. The calculation method are each step. Yes. But do not change things more, just be aware that later on. Yeah. It's slightly different. And if you do things like that for research, you may immediately measure angles and distances and see how they're different. Right now, we don't care about it. So let me check. Yes?
So what are you trying to actually
we're always asking, why do we optimize? So some researchers do nothing except geometry optimization. What is geometry optimization? When distances between atoms and angles come to most natural values. So if I draw things by hand, then it is not ideal. I can put something further or closer. And through optimization, it moves times until the total energy is minimized. So in chemical sense, it finds the most stable configuration for mode. Make sense?
Yeah.
Okay. Let me check for everyone on the everyone on the online if there are questions, and if you did arrive to analyzing of the .log optimized file. So,
Professor, so you already download that
what?
you
Just please repeat the question.
Kia, mute one of your laptop.
already.
Yeah, correct.
Okay, Professor. So first you download that file in.
No. So here is the procedure. First, I create it by hand.
Okay.
Second, I save it. Third, I submit the job. And fourth, I open the results file.
Okay.
So, since because of this graphical tunneling, I'm not up and downloading things. I'm working completely on the remote foreign server.
Okay.
So let me check with everyone if.
Quick question: what's the abbreviation? What's the name of UFF?
So may I ask Sarah to answer this question? I'm confident she knows. Lina is asking. What is
Hi,
it?
Sarah. I'm asking what UFF goes for. It's abbreviation for what? UFF.
Universal force field?
Universal force?
Force field.
Force what?
Force field.
Field. Oh, okay. Thank you.
Yeah. And here is Lola. You can just say it. Okay. Yeah, thank you, Sarah. So, may I ask Boston to share screen? First I need to enable everyone to be co-hosts, just quickly. Except myself. Make co-host. Yes. Make co-host. Yes. Yes.
Which screen do you want me to share?
Yes. I want to see your Gauss. You just share your desktop if there are no secrets. Bring it to the front. Gaussian calculation setup. I think it is behind. It is at the bottom.
This one there.
Yeah, this one. With the mouse. Where's your mouse? Slow. Just. I'll suggest what to do. Slowly. I can.
There we go. I'm sorry. I was muted the whole time. I've been trying to talk. Sorry.
You need to go to the left side. Then behind that there is an window. Another
This
window.
one?
Yes.
Yes.
You can close it. You do not need it. This one you can close. And now please try to find on your screen the Gaussian calculation.
Yeah, it's up. It's on my second monitor, but it won't let me move it to the one that I'm sharing.
Please bring it here to this
Yeah,
monitor.
I've been trying to. It won't let me move it. I can maybe
close it there or move everything to second monitor and then share it. And make sure that all things are together.
So let me just do this. I'm gonna move everything to one monitor. All right, are you seeing things now? And then
no, stop sharing and then start sharing again and select another monitor.
And then
okay,
calculate Gaussian setup. You seen it?
Okay, good. Now mechanics, UFF, go to job type, yes. Energy optimization, you need to select optimization. And that's it, do not change anything else. Now go to submit. Submit, save. And maybe make UFF 2 because it's your second attempt. Just add number 2, save. And now click OK for submission. And just wait, practice patience for a couple of minutes. Now select the .log, this one, OK. And now immediately go to main panel of the Gaussian, and click, summary, and enlarge it. And you see the total energy minus 0.009 something.
Yep.
Total energy.
Mm-hmm.
And if you carefully watch, the interatomic angles are slightly different after your optimization. Okay, you are in a good standing. You can stop sharing, and let me check if Kaya wants to share screen.
I'm just able to log in there because my laptop stopped working then.
Is it on charge? Is it connected to the plug?
Yeah, it's now connected.
But please try to connect and do same thing as everyone. So do you have Gauss U up and running?
Yeah, I
just where is? If Gauss U is not running, please start it. Gauss U gview.exe. Add this ampersand shift 7.
Yes, shift 7. Then enter. But the thing is, Professor, I'm not able to see that file. And that's why I'm asking you. I create a lab4a.
Just wait. You need to practice patience because of the connection. Yeah, we are in time. I think in like 5 minutes we all will be on the same page and we'll continue. I think if you click on the advertisement panel, it will disappear. Yeah, advertisement, the title panel, Gauss U 50. Click on it so that it disappears and doesn't block anything. The logo, the symbol.
This one? There?
No. Right in the center. Right in the center of this. Yes. Now, did you create the file? Let's try. Maybe you already have it. Let's go to main panel. Main. No.
There? This one?
No, the main control panel of the Gauss U.
Okay.
It is behind. Yes, here. Now click File, Open, File, Open. You have nothing. Okay, now you can close it. So it means you need to draw a file from scratch. So in the periodic table, select titanium Yes, quick, quick. Now select tetrahedral. Yes, yes, quick. No, you didn't click, you need to really click, yes. Now go to this white panel and click once again, quick.
I don't know sometimes why it's not working.
Okay, now it works. You need to click more confident. Like maybe
Okay.
hit the button. Now let's go to periodic table.
It's already gone again.
Oh, I see, I
Bad-
see. Maybe,
Bad.
okay, please try to, I believe the problem is that it takes too much of the bandwidth. So please mute your camera on both of your laptops. It takes too much of the information. Mute the camera while we are making this demonstration, and then things should work better.
Okay, Professor. No, now it's segmentation.
But did you mute the camera?
Yeah, I use the camera.
No, please mute, please disable the camera on both of your laptops right now.
Okay, both of the camera.
Yes. And the second one too. Because video information takes all the line, and there's also a disable camera on the one you're watching right now on the second laptop.
I'm trying. Sometimes my laptop.
No. If you select zoom, control pad, zoom symbol at the bottom. Yes, here.
Okay, there is options.
You can tell for a second. Oh, okay, yeah.
Now.
So let's do once again.
Titanium.
Again.
This one. Then click.
And now click here. Confidently click.
Okay.
Hit.
Oh.
Okay. Now in the. No. Do not repeat. I think there are some technical problems. If you will come into the lab or
will come to the lab. From the next day, I will come to the lab because
come to the lab or in your office. Like come to the campus at least. Here, internet is quicker. Now, do not do anything. I'll give you quick instructions as I did for Sarah. Even do not stop connection. I will be back with you in really quick.
Okay, Professor.
Just wait.
Okay.
Okay. Remove this Gaussian. Just backspace. Do LS.
Okay.
Enter.
Then enter. Yes.
Yeah, just go to your black screen, to your terminal.
Okay.
Do not touch Gaussian right now. Go to the terminal and hit LS, enter.
Enter. Yeah, now I am able to.
You see, I just copied this file to you. Now please type G09.
G09.
Not O, not like a letter, but like zero. G09.
Oh, G09.
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 Space. And then just hit the tab button that it will repeat the name of the file. Yes. And now hit enter.
Okay.
Now type ls.
ls space lt.
Just ls, enter.
Okay.
So what do you see?
I'm able to see the name of the file, and it's in a different. It's a .chk.com and .log.
So make more more space more space, and then name of the file that ends with .log.
Which one? This
Copy the last of this three.
copy. Okay. Copy. Control C.
Just try once again.
More. Control
hit the tab button. Hit the tab. No, it doesn't continue.
Professor.
Okay. Try to
now
enter. Enter.
Yeah.
And hit space. Hit space. Button space on the keyboard.
Okay. There.
Space.
Of space.
Space.
Okay.
Space. More.
Space.
More. Space. Space.
Okay.
Space.
Space.
Continue.
Again a space.
Again, yes. Space.
Okay.
Again, space.
Mm-hmm.
You already over more than half. You see, stop here. In the middle, you see energy equals and then a number.
Atomic number. Yes.
No, the word energy. Do you see word energy?
Yes, energy minus 9.34.
Okay, so it is one of the intermediate energies, while the program is doing the same thing as we did yesterday in the class.
Okay.
So it browses through potential energy surfaces and comes to the minimum.
Okay.
If you keep hitting space, at the very end, there will be last time this word energy appears, hit more.
Space again.
Yes.
Space.
Space again.
Then,
space again.
Yeah, I think.
Maybe scroll a little bit up.
Okay. This one? This section?
Scroll more up.
Okay.
Stop.
Okay. Predicted change in energy. Minus 2.
Decision complete. Let's scroll a little bit more up.
Okay.
More intuition. Stop.
Yes.
Okay, I just don't want to waste your time, but let's go to, there are two ways to find it. Either scrolling through this big file and find correct word, or you can go to the main panel of the Gauss view, which I think is working now. Main panel of the Gauss view.
Just a minute. This.
The main, not, yeah, this one.
Okay. Then file.
So file open. File.
Okay.
Open.
Open.
Just wait.
This one.
No. Go to the file type below. File. No. Back to lab4a. Click. Now slowly.
Okay.
Please slowly. I'm becoming nervous. Please do not move it so quickly. Slowly, gently move the mouse down.
Okay. This one or
down. No, down. Just move mouse down. More, down. 2 inch more. 2 inch more, down.
Okay, this one.
Stop. Click. So and wait. The second option. .log.
This.
No. Up one. No.
Just
click once again. This one, yeah. .log. And now click on this here. Yes. Click.
Then
open. And open.
Slowly. Yep.
Open.
I hope it will be
and
working.
Go back. No. Do not.
Okay, this one. Okay. Then.
Do not touch anything.
Okay, I will not touch.
Please go to the main panel.
This one.
Yes. Now go to results.
Results. Yes. Then
And
summary.
click on summary.
Yep.
Wait. Maybe make this window a little larger. Look here, total energy minus total energy, about in the middle. Yes.
Minus 0.009340.
Yes. So it just saves our time in browsing through the big file. It parses right word. Okay?
Okay.
So you can stop sharing screen. Now we are on the same page. I will do next demonstration and then come back to go around everyone.
Okay, thank you.
Sarah, you are still ahead of the whole class. You have the things that we will arrive to in 20 minutes. Share screen. Gaussian. There are too many files. I do not remember which is which. I'll navigate through Windows. I think we did this by hand optimization. Yes. So this is the result of optimization by universal force field. Now, I believe that this geometry is okay, and I want to go to our actual goal, electronic structure. So first, I activate this file, this structure, by clicking on this panel, bringing it to the front, and then, without clicking on anything else, I immediately go to main control panel. And there I click on calculate, Gaussian calculation setup. So this panel should pop up in the front. And by the way, you see that on the top it types opt, which means optimization UFF, optimized by universal force field. But now I slowly move the mouse. You see, slowly move the mouse to the word mechanics. I click on it, slowly move it down, pass semi-empirical, and click on hard fork.
What is hard fork, Professor? What's the
Hard fork is the method for electronic structure to find total energy, to find ground state of all electrons and find energy of this all electrons. This is the energy that is later used for optimization. And for UFF, uses some pre-calculated constants, and it works okay for like carbons, hydrogens, and oxygens. But if you go to like uranium or lanthanides, it may fail easily. There are no force fields for heavy metals, so the electronic structure methods are more reliable. And by the end of the class, I want everyone to be a universal researcher, not only bound to like carbons and hydrogens. So just a little thing that, so here is my mouse on hard fork. Now I slowly move it to the left. I keep ground state, I do not click, I do not change it, and I move a little bit down to the word basis set. So I see this 3 minus 31G, I click on it, and I'm slowly going down, until I see level 2DZ. We will go over all the things in the class later. Right now, just try to follow.
So, Professor, why we need to set this one? And what's the
This 102DZ is quite good for transition metals.
Okay.
But we will discuss what is basis set. It will take us time. It will take like 2 weeks of lectures.
Okay.
Now I slowly move mouse back up to the job type, and I click on the job type. Now I want to go to optimization, click, and change it to energy. So, which means I do not want to optimize. I want to compute single point energy. So energy means positions of ions will be fixed, nailed down, and we only compute electrons. When someone computes optimization with electronic structure methods, it's also a good and legitimate method, but now I want to simplify the problem and avoid unnecessary time. If you would optimize models with anything else than UFF, it will scale very expensive, especially for big models. It is okay for this small model, for everything will work in 2 seconds. But I just do not want to give you a false impression that you can take 2 million atoms and optimize them with electronic structure methods. No, today's computer power will not allow us this. So after this, I slowly go down to the word submit. Okay, click. It tells you must save Gaussian input file before you submit. Would you like to save and input file now? Yes, I do. So I click save. And then it brings me an opportunity to change the file name. So so originally it was by hand, but now I do just energy. I can write energy, or I can write SCF for self-consistent field, or I can do nothing and then put HF. You do not need to do this long name, but generally, during this class, we will create like 500 files. And if you do not name them, they will be completely unbrowsable. So I change the name and I save. And after it tells submit the following file to Gaussian, I will answer yes, and let me give a quick comment. What we did with Sarah and what we did with Kia by typing G09 space and then input file, it is equivalent to the command that we are doing right now.
Yeah.
Submit the file to Gaussian. So by mouse clicking, we are just transferring control over this model from this nice graphical Gauss view to more serious command Gaussian, which is typically has only command line interface. So after I click OK, I wait, count 1, 2, 3, and it is ready. It is only because the model is small. The bigger the model, it scales in best scenario as number of atoms cubed, but typically even worse. So if 100 atoms computes in 2 days, then 200 atoms will compute in 8 days. So this growing function, disproportionate. Now it tells me Gaussian job completed. Would you like to open the following results file? So I select the second one that is named .log. I click this .log and click OK. It will bring the same model up, but it will be a new window. Again, I'm practicing patience and not clicking anything. Because if I'm disorganized and I have like 10 other models, if I click on the other model, when I go back to main panel here, it will facilitate me to analyze results for another model. Whatever comes to the front will be analyzed next. Then again, I need to learn it myself. Slowly move to this main panel, go to the button results, and click summary, same as you did before. And it looks in a similar format. So even if you do not know what Linux is, you can operate it. And right now we are suffering this little discomfort of connecting to a remote server, which sometimes doesn't work for graphical work, just to save some funds. If like university and my grant support would be unlimited, the best thing would be to just purchase copies of GaussU and Gaussian and install them on each computer. It's kind of expensive, and if you decide to do it for your work and you have any funds, the Gaussian is like a couple thousand, and GaussU is like something less than 1,000, maybe 500, which is okay. But if you do it for everyone in the class from one point, it will be a little too much. And through this little trick of remote things, we get things quicker, cheaper. Okay, so you see there is a line that corresponds to energy, and it shows different value. So depending on the method, absolute value can jump drastically. But if we will make relative energies and change positions of ions and recompute, the relative changes of energy will be very similar in most methods. So the absolute we need this total energy from eigenstates of ground state, eigenenergy of ground state of all the electrons, because it is needed for potential energy surface. But for potential energy surface, we need like shape and curvature. If you shift everything up or shift everything down, chemistry doesn't change. They're chemical properties. So our minimal goal for today's meeting was to get this number. And we still have time, and I will try to go to the maximal goal. But please be prepared, be aware that there will be a homework asking you to take several models and run same type of a job and report analogous number. Okay? So let me show something more on the same line, and then I will visit the seats and ask to share screens. So what if my graphical connection is not working? What if I do have geometry as Cartesian coordinates, but I can connect only from the command line? So here is the file that we just saved when we here is the file that we just saved by clicking through this Gaussian Gaussian job submission button. And if you look inside this file, and now we arrive into the same stage where Sarah was an hour ago.
Yeah.
So we do see the following thing. So this is important but secondary. This second line is really important. So it shows the choices that we did make by mouse. It shows HF particle / line of PDZ for basis set. Then there are some additional things which I explain later, and then there are Cartesian coordinates of the atoms.
Yes.
So in some sense, one can just put Cartesian coordinates in the file by hand, and then place the top line, and then submit the file to Gaussian without any graphical connection. Now, let me copy this. Let me copy this file once again, so that you see that I'm not doing any hocus pocus. It's all fair game. So I'll just call it test.com. And there is only like this test.com file, but there is no log file. So in a narrow sense, in a very narrow sense, even telephone public, the goal of Gaussian program is to convert .com into .log, right? We type G0 9 space test.com. Wait a little. 1, 2, 3, and then it comes back. Now I type ls-lt once again, and you see there is a file test.log appeared here, which was not available before, right? So this file contains results of electronic structure calculation, including total energy of the ground state of all electrons. From Gauss-U panels, I remember it was something minus 359 atomic units. Let me check where it is. And I need to be prepared and practice patience because the file, as you see, is substantially larger. So test.com has 700 bytes, which is like one page. And test.log is 16,000, which is like 30 pages. So I click more and then hit space, same as Kea was doing. So I hit it several times and just get acquainted. And when I arrive closer to the end, but not at the very end, I will see this SCF done E RHF. So let's compare to what I see in Gauss-U. E RHF, restricted Hartree-Fock. So minus 359 point blah blah blah. Here I have the same minus 359 something blah blah blah. So I would need this to parse this line out of the file because I do not want to scroll it again and again. So let me do grep, which is parsing. SCF test.log, and then it brings this SC only this line. So it is the way to extract the energy from the file. So from now, I would like to visit with everyone and check if you successfully arrive to the same stage of getting the total energy both in graphical and in text form. When you can do this shift 7. Don't do it right now. 12, 10. So it continues. something that is not just means. Huh?
I didn't do that. I didn't feel it. How it's shift on what?
No, 10. It just helps, like Siri on iPhone or Alexa on. It just tries to read your mind. Okay, so you got the number, right?
Yeah, so on your iPhone, but
Okay.
on one.
Oh, that's okay. That's okay. It doesn't find spaces. Try to. Boston, would you like to share screen?
Yeah, I can do that. Hold on.
Thank you. Okay, and can you show the stuff in the command line? Enter. ls minus lt. And let's first do just more space, and then the file that ends with log. Titanium 04H4 energy HF. Yeah. It's not the bracket, but
There we go. Right button.
but if you type, just follow whatever you gave a name. Titanium 0.
I must have hit 0 in my.
That's fine. That's
Whoops.
fine. Energy. E. Energy. Dot log. log. Enter. And if you scroll through, just hit space. So in this information, you can find what we need, right? It's about here, yes, SCF done. But let's do it in the elegant way. Let's do it. Please type the arrow up, then arrow left several times, and replace the word more with grep, G-R-E-P, space SCF uppercase, SCF uppercase, self-consistent field, space, enter. So you see the number that we need, right?
Yep.
Okay, you can you're fine in a good page. You can stop sharing. Kaya, would you like to share your screen?
Just a minute. What is the share screen? Sometimes. Share screen. This. I already did, but I was trying to do that one. GREP, then this after.
And now type the name of the log file.
Okay. This
Replace
Log.
LG enter.
Enter.
Yeah, there is the right number. Very good. You are on. Yes, excellent, excellent. You can stop sharing.
Stop.
Sarah, would you please share a screen?
Yes.
Okay. And can you please, enter? Yes, you're doing great. Thank you. You can stop sharing screen. I'm really happy. Everyone is progressing really well. So since we are ahead of time, I would like to introduce the concept of orbitals. And depending on the time, we can go on with their energies or maybe to their visual representation. And next time we meet, we will go through the so-called concept of so-called density of states. I know that Steven has connected and he needs this one, although he has all skills, but he won't still use it. So please let me check if we did hear the word, German word, Aufbau principle. Aufbau, build upon. Anyone? Oh, did you hear about it?
Yeah.
Can you tell what it is?
So it's just the principle that explains the arrangement of electrons in the k element orbital. So I know it's about k element orbital, like how to arrange electrons in each of the orbital, but I don't know that.
Okay, yeah, excellent, thank you. So, and I will repeat, don't worry, you will get through it all together. So, when we are looking into periodic table, then you know that as we go from number 1, number 2, number 3, it has more and more letters, right? And when we have, for example, carbon, chemists do this way. 1 is 2, 2 is 2, P2, right? You recognize this recording. Or some people do for S orbital, it's up down, and then next show and does for S up down, and for P one gets this way or this way, right? So it shows how we feel an ion is the ion of specific element with electron. We put them on different orbit. The key part of the stuff is so-called Pauli exclusion principle, which means you cannot put each more than 2 electrons into one quantum state, right? So if we want to find the total energy of an object, atom or molecule, we need to find energy of the first electron, then energy of the second electron, then energy of all electrons up to the last one, and then add them together. It is not quite correct. I will tell that there are some corrections because electrons interact with each other. But in very basic form, we need to go over all orbitals that construct our atom or molecule and add energy of each electron together. This will give us the total energy. So what I'm going to show right now is not a correct theory. We will learn correct theory in on lectures in class. Right now, I'm doing some cheesy, quick style explanation. Let me check. Someone is typing. Maybe someone is criticizing.
No, it's not criticized.
Let's check mine. Just a second. Kia types, I heard this when I was in high school. Our principle shows that electronic state like electrons fill in the lower energy atomic orbitals first before filling the high energy. If you don't mind, I'll share because your typing is really great. Okay?
Yeah. Share it.
It just it competes with my other windows when it doesn't want to show this chat line. But what Kate did type is it was really correct. Maybe you can read out loud your writing yourself.
Sorry?
Kate, will you please just read what you typed yourself?
Okay. Actually, our principle is like that. It shows the electronic state. Like first electron, it's like a fill up the orbital. So in first electron fill up the orbital in lower energy atomic state. Then after that it fill up the higher energy state. So actually our principle is like it shows electronic configuration for atoms or ions. So I think we already know these things and we studied in our high school.
Excellent.
Chemistry.
Yes, very good. And now we will make connection between this basic information and some let's say advanced computational chemistry method. So this is not for saying in public, but it will help us understanding of how things are going. Now I'm going to show once again to scroll through this log file, and I would like to bring your attention to the place that shows this thing. Initial gas orbital symmetries, occupied and virtual. So please try to go to this spot in your file, and then if you hit, maybe instead of space, one can hit enter to move a little slower.
Yeah, we already get.
Yes, this is the right spot. So please bring it up on your laptops and terminals. So please tell me what do you see, especially about the numbers. Just share your observations and do not hesitate.
So AU there. Okay, I can show.
Yeah. Can you tell what you see?
Yeah, I can see the eigenvalues, it seems, for the electrons in the molecule. And the eigenvalues means the energy of state of each electron. Maybe.
Yeah, makes sense. Next. Sarah, let me ask you, do you see that there are two types of orbitals, two types of eigenvalues?
Yes.
What are they?
The occupied and Wirt.
So how do you interpret what it is?
Excuse me, what was the question?
How do you interpret this notation? What is occupied and what is virtual?
I think the occupied has the least energy.
Yes. And what does it mean, occupied? Who is occupied? Like one country has occupied another country by military force. Is it related here? Probably not. So who is occupied at what?
You mean the which orbital? The
Right.
s orbital. The s orbitals are occupied.
Okay. And then there are several occupied orbitals.
Yes.
Yes. And virtual are unoccupied. Okay. Yeah. Good. Thank you. Thank you. Well, do you have any observations? If you look on the if you look on the values that you see in this table, are they random? Do they decrease? Do they increase? They increase. Yeah, thank you. It's really important. And Boston, I apologize, I don't have a question for you, but I'll ask you something next time.
Sounds good.
So, the
So we have negative values for the occupied.
Yes.
So the eigenvalues
Uh-huh.
are negative, which means attractive.
Perfect. Yes, correct. And I heard Boston was to say something.
Yeah, I was gonna just ask a quick question. So on your screen, when it's the occupied and virtual orbitals, all of them are showing A. For mine, they show different values. It shows E's, B's, and A's. Did I do something wrong, or what's that significant of?
For now, do not worry. It's about symmetry of orbitals, and right now we do not care. We need just basic things, and what I saw on your screen was fine. So, but you have a good eye, and you can return to this aspect later. So, first, yes. Second, yes. Then what do you have? The sound is just too close to the screen. I will just disable sound for a second and then. Okay, I'm good. So you see this little drawing that I did, right? And the cells in this diagram do exist independently of whether I fill them with electrons or not, right? So the filled cells are occupied orbitals, and empty cells are virtual, unoccupied. Make sense?
Yes.
If you take notes, which I don't, but you may just write it down. It's one of the important things. Memorize it is easy. There is one important correction. In this little silly diagram, I was showing atomic orbitals. Right here is example of carbon atom. But we are speaking about molecules. And in molecules, instead of atomic orbitals, we have molecular orbitals. It's still electrons, but they can find an orbital that is spread over several atoms, right? But it's still, one composes many electronic states by placing each electron on its appropriate orbital. And since each molecule has limited number of electrons, we just count how many atoms, how many electrons per each atom, and then that's it. So it is limited number of electrons. And we compute molecular orbitals and fill them with electrons. And then approximately, again, with some additional corrections, we add together energies of all occupied orbitals and get total energy of the molecule. So if we make an exercise and take these numbers together, -20 plus -20 plus -20 plus -20, and add together all these numbers, we should get something close to this -359. If it is not exactly, there will be responsible procedure is electronic repulsion. And if you see if it is substantially big, it means electrons repel each other noticeably. But just approximately adding together is roughly the total energy of the system.
So that's
Yeah.
one minus one.
The rest
So
of
the
it,
rest is
the rest is electronic. Yes. So, but in order to compute, so for solving our main problem for getting total energy of ground state of all electrons that are filling the model with our ball principle, we need only field occupied orbital. But in order for theory, for this Hartree-Fock method to work, one also needs unoccupied orbital. They just integrated part of the calculation. And let me, again, we will dedicate like 3 weeks for this method. I will repeat many things in more rigorous way, but in a very simplified, approximate way, there will be different procedures. One procedure to compute orbitals and another to fill them. So when we recompute orbitals, we do not know whether certain orbital will be occupied or unoccupied. So first we compute them, and then we fill them by the electrons. So it is needed to compute the orbital. So any questions on this aspect?
So I have just a question. So we said this is the basic principle that we use. It's not accurate at the reality. So we will then use some other approximations or different models later.
Okay, thank you for the question. There, as you probably realized from the lectures, there are no precise methods.
Yeah.
Anything in computational chemistry is approximation.
Okay.
And Hartree-Fock is like starting point. I wouldn't say it is the simplest, but one of the simplest.
Yeah.
So it has some approximation. But all approximations are rigorously defined. Right now, when I'm speaking, I am doing more like, right now I'm doing popular science instead of regular observations. So only that you get basic concepts. Later, starting on Friday, I will be careful and rigorously for like 3 weeks deriving steps, what means what and how we get to it. But now, so we can understand what we are doing, I'm explaining things on a popular level, skipping multiple details. Otherwise, we will not fit into that. Cool. So there is an important. Oh yes, please. Yes, hold.
You're saying like this is not the energy value, right?
Yes.
Okay. For the occupied ones, are we able to identify which orbitals they are?
Yes, excellent. And, I really like the question, and we are on the same page. So, in a very narrow sense, computational chemistry is just solving this problem. And the best way, if you do this calculation, the best way to present the audience is to show these orbitals how they look like in space. And there is a substantial number of people who are really emotionally attracted to drawing, watching, and showing orbitals. And I definitely will show how to do it, and it will be one of the subjects for next round of presentations. Yes, your question is very relevant.
Okay, so like the other thing is the virtual value. So if we're saying the virtual one as a one that amounts of 5, or value like 1 point, what's the significance? What does it mean? I mean, if it doesn't have electrons in it, is that the meaning of virtual?
Okay, so
the numbers simplified.
Please, I really like this style of
I'm guessing that if you go further from the nucleus or further from the we mean the higher energy state, so it will be 1.7, for example. So it's the highest energy state, right?
Okay.
I believe minus 20 is the most attracted one to the positive charge.
Yes, it's the core electron, which is typically probed by X-ray methods.
Oh.
I really like how we arranged the discussion. It's much better than myself mumbling something. So we go up in energy from lower energy to higher energy. This way, the next line, right? And there is an important thing. It's technical, but these calculations are done in so-called atomic units or Hartree units. It's like easy to remember. Hartree Fock is done in Hartree units. And Hartree unit of energy is 27 point something electron volt. And electron volt is a standard energy measure for physics. Like visible light is approximately 2 electron volts, okay? Which will be 2 out of 27. Will be like 0.15, something like small fraction. Okay? And minus 20 will be like about minus 500 electron volts. With soft X-ray LE experiment or several X-ray experiments. Most important chemical properties of molecules are depending on the energies and shapes of the orbitals when we transfer from the last occupied to the first unoccupied. So these two energies are really, really important, because when we excite a molecule with light, we will promote electron from this orbital to this one. So the energy difference between these two orbitals define the color of the material. Right now, if I take this minus 0.5 and it's about 0, the difference is about 1/2. If I convert it into the from atomic to Hartree-Fock, so 0.5 times 27 will be like 0.13. This is much more than visible light, UV, which means this titanium hydroxide is transparent for human eye. And if you did inorganic synthesis of like nanoparticles, the titanium hydroxide is available. It can be dissolved or it is transient in some directions, and it's indeed transparent. It doesn't have color. So qualitatively, what we see here already makes sense. And do not worry, we will come through this main observable main connection between calculations and real life again and again, because it's the goal of the course. Another connection of this orbitals. If you are doing electrochemistry experiment, does it tell something to you? Electrochemical cell, when you do oxidation and reduction, yes? Can you tell more what it is? Just briefly, because most of us here are not from chemistry, my degrees are in physics. So if you teach us what is electrochemical oxidation and reduction, we will talk.
So, in electrochemistry, basically, you have a solution and electrons are trying to travel down. Okay. So you have a positive and negative end, cathode and the anode. So electrons are trying to move from the positive end to negative end. So oxidation occurs on the anode. I'm not really sure if and then reduction happens on the cathode. So that's why most times when you see chemical elemental equations, you see something like aluminium, it's trying to break down into the aluminium 3 plus, it's trying to break down into the aluminium element itself plus, trying to use the 3 electrons. So it's just basically electrons trying to.
Very good, very good.
But I would also use salty solutions, which in the liquid or in the water, it gives positive ion and negative ion. They can move to the different charged electrodes, as Maulana said. And then through that process, the electrons will be lost or gained on these electrodes and make a electric current inside.
Okay. Yeah. It's all correct. Yeah. Thank you. There, in as a little addition to what we told. So there are two different. I know we are far from computational chemistry. It's more like basic popular science. But in addition to regular electrolysis, when ions or molecules lose or gain electrons on the anode and cathode, there is an analytical chemistry technique when one places a molecule in between, and reaction happens not on the electrode but in between the solution, and one applies different value of voltage between anode and cathode, and depending on the molecule, it will either lose or gain an electron at a specific voltage. And therefore, as you scan voltage, your current will be not like Ohm's law, will be not continuous, but it will have spikes and dips when the molecule in the solution gains or loses electron. So this oxidation and reduction electrochemistry is part of the analytical chemistry class, and there are really nice. It is an analytical chemistry. IV characteristics is a signature of a molecule. So if you synthesize unknown molecule, you can do optical stuff, or you can do NMR, you can do mass spec, and you can bring your sample to electrochemistry cell, scan the voltage, get this IV curve, and then look through the tables. So the publications what this IV curve corresponds to. So it's a way to identify a molecule by its signatures. And the energies of this occupied and unoccupied orbitals, they exactly show at which voltage the molecule will lose or gain an additional electron, where the spikes in the IV curve appear. So by computing this electronic structure in these orbitals, one can immediately predict electrochemical characterization of a molecule. I do not want to go too deep into this, but if you are more in physics background, you could be aware of the scanning tunneling microscopy experiment. So you do IFM, and there is an STM.
I haven't tried this yet, but I know how it's.
So it also it's very similar to electrochemical experiment where when one applies voltage for molecule on a surface in vacuum, and through tunneling one also gets charge by removing occupied electron from occupied or putting electron to unoccupied. So it's also a way to characterize a material. So I do not like on my clocks we have only 9 minutes left. Maybe you have some plans for evening, but I'll declare plans for the future and maybe do quick demonstration in a few minutes remaining. So I want to believe that you got some interests and understanding of the value of these orbitals. And I will include into one of the future homeworks and asking you to compute this value of occupied and unoccupied, subtract their difference, and make an analysis telling whether the material molecule will be transparent or intransparent. It's kind of easy. No, the right, Laura, I have the right word. But ionization energy and affinity energy. So if you remove electron from occupied with ionization, if you place electron to unoccupied with affinity. Cool. I've got my pass chemistry. So there are two aspects in analyzing this calculation. So one aspect that Laura already brought up, we need to learn how to draw these orbitals. They look really beautiful as three-dimensional pictures, as balloons in space. So it's one aspect. Another aspect. Here we have a molecule of only 9 atoms. It's really tiny. And we already have so many orbitals. What if you take 100 atoms or 1,000 atoms? Number of occupied and unoccupied orbitals will be not possible to watch on one screen. But since many of us are involved in material research, we do need to characterize models with substantial number of atoms. Like if you are doing biomolecules for solids or polymers, like bio is Lina, solids is Boston and Sarah, and polymers it is what Kay is doing. Those are really big molecules. For chemistry, what Law is likely to deal with for research, size of molecules are typically a little smaller. So one can do abundant chemistry with less than 100 atoms. But still it is a lot. So there is a way to compare and analyze this energy profile of a molecule without looking on this table of numbers. There is a way to combine them in one integrated image that is called density of state. And on this image, one will see the energy offset between these two states as a little empty space. So I'm going, we probably do not have time for practical things, but I'm going to show demonstration of how this density of states image should look like. And then I will start preparational steps for molecular orbitals. And then we will be done.
So next week we have a presentation or something?
No, wait. Presentations will be in like 2.5 or 3 weeks. We don't have enough material to present.
Okay.
And I'm going to show a list of, it's not a secret, list of materials that we need to cover. So this is what we will be doing next Wednesday. And this image is literally density of states for the molecule, for the titanium hydroxide molecule that we just considered. Remember, it was 0.5.
Doctor, what is DOS?
DOS is density of states.
Okay.
So each orbit, each molecular orbital is interpreted as a state with its own energy.
Okay.
And density means how many states per energy interval.
Okay.
So in the table that we were looking at,
The states, so the number of the states
per,
this
per energy
energy.
interval. So I can come back and show the table once again, but remember, lowest or highest unoccupied was minus 0.5. And if you convert it from atomic units to volts, it gives you something minus 13.
Professor, I'm sorry. Could you
Yes,
please? I'm not able to understand this figure. Could you please explain it? Just a few words.
yes,
It's
absolutely.
already 7:55 p.m. But
Yeah, sure. And do not worry. Most of our next Wednesday lab will be about this figure.
okay.
And in some sense, building these figures will be the main practical skill of the course. So I guarantee everyone will build these figures at once. So let me bring just for a second the table. And you see that energies here are going in the ascending form, from lower to higher, right? And then after we go from occupied to unoccupied, it's minus 0.5, this is 0. And then they keep growing. So I focus your attention only on two orbitals, minus 0.5 and 0. So minus 0.5 times 27 will be minus 13. Okay? It is here. So this peak corresponds to highest occupied orbital, energy of highest occupied orbital. Right? The first lowest unoccupied has energy 0. 0 times 27 will be 0. Sure. So these two peaks correspond to frontier occupied and unoccupied orbitals. And the energy offset between them determines the color of the material. Also, this value of occupied is ionization energy, and energy of unoccupied is affinity. The meaning of this figure, so x-axis is energy, y energy is how many states. There's only one state, therefore it's one peak. If there will be too many peaks compressed, it will become continuous and a little forward. Right? So the value of this figure is that even if you have 1,000 atoms and 5,000 electrons, we still can do this figure and analyze and immediately say what is the power, what is ionization, what is affinity. As humans, it's hard for us to read through several pages of numbers. We're not computers. But you can get basic information just looking on the figure. And it is quite a comfortable format to analyze basically any material. Make sense? Okay. So I believe we are done, and I would be happy to stay here and show more, but maybe you have you either tired or you have plans or you are hungry. So let's probably finish it for now and postpone considerations. Let me maybe last thing, and do practical things, but so that you do not feel surprised later. So it is in one of the files I did send you before the meeting. And here is a list of subjects to be presented next time, the next presentation. It's not in 3 days, it's like more in 3 weeks or less. So it's basically our plan of study for next 2 labs. So today we covered partially this spots, and we did analyzing Gaussian online output.log file without Gaussian. We did it. We discussed total energy, ionization energy, ultimate affinity, homologogram. Right? So, right? Yeah. So it's basically what you do. HOMO gap, HOMO is highest occupied molecular orbit. LUMO is lowest unoccupied molecular orbit. And density of states is in the list. Molecular orbitals was lower than us also in the list. So we'll cover all this. Okay, enough for today. Thank you for your interest, for your questions. And
Next presentation 3/5/18. Oh, no. It's
do not look on it. It's from previous years.
Okay.
I will tell you more details about time when we go through the labs. So maybe third Friday from now, if everything goes well. So we do 2 labs more and then present.
Okay, sure.
Okay. So meeting is done. Everyone is welcome to depart or disconnect. And I'll stay here just in case there will be some questions. It's very optional. Please, let's maybe let's wait if there will be something. If anyone else signs up for more questions, and I will.
Excuse me, Professor, for
Yes.
the next lab, should I come to the class in person?
It's
Yeah, I think it's better.
It's better, but you will need it only for next 1 or 2 labs. Then you can stop coming to the lab again. The rest of the labs and course can be done without graphical tunneling.
Okay, thank you.
So we will need it for plotting molecular orbitals primarily. We did need it in the past for building models and running Gaussian in the mouse-operated format, and we will need this graphical connection for plotting molecular orbitals.
Okay, thank you.
Okay.
Quickly check if Boston or Steven have quick questions. No? Boston?
Boston already said something. Can you use DSO to determine the band gap of material and whether or not it's a direct or indirect?
Thank you, Boston. Well, I will answer this question because they are related to the labs. I have some other questions that are related to this lab, and later I will be with you to answer your question about the reaction. So, for a question from Boston, yes, the energy offset between HOMO and LUMO is the band gap of material. And let me check. I have forgotten maybe the most important things for physics. The energy offset of HOMO gap also determines whether the material is metal, insulator, or semiconductor, right? So when it is really big, as we saw today, like UV, more than 10
would be
insulator. When it will be about 1 electron volts, 2 electron volts, it will be semiconductor. When it will be 0, then it is a metal. About direct or indirect, the calculation that we are doing right now will not show difference between direct and indirect. But when we will be done with Gaussian, and in 3 weeks from now we will switch to bus, the dependence of energy of orbital on momentum will be introduced. And then we will see difference between direct and indirect semiconductors.
Okay.
Make sense?
Yeah.
Yeah, thank you for the question.
Yeah, I've been trying to work on it myself actually, so I was a little bit confused, but
Yeah, we'll go over it. It's planned part of the class. And for momentum dispersion, we will focus on nanowires rather than 3-dimensional objects because it is much simpler.
okay.
Let's check. What? Band gap? is the same as homology. Why the word bandgap is used? There is no conflict between physics and chemistry, between physicists and chemists, but there are slightly different words in the communities. So for small molecules, there are discrete orbitals, and one just tells energy of set between HOMO and HOMO. In physics, often people deal with systems which have like too many orbitals, like more than 1,000. But there are very, very similar orbitals that have the same shape of electronic distribution in space, and they change just slightly. So they form like a family, a band. And in this sense, physicists call like all occupied orbitals valence band, and all unoccupied orbitals conduction band. And energy offset between them is referred to as band gap. But it is absolutely the same as homology. So I will keep my promise and answer to Laura, and let's check if Kay, do you have quick questions?
No, I don't have any.
Okay, then I'm going to talk to Roland because she has some questions related to last lecture. Everyone is welcome to disconnect and depart, but I'll stay here to chat and answer questions.
Have a good night, everybody.
Yeah, good night, Boston.
Thank you, sir.
Thank you. Goodbye.
Thank you, Sarah. Goodbye.
Sorry for being late.
Oh, that's okay. That's okay, Steven. I know you're an expert in all these things.
Bye, Professor. Bye.
I'll keep it on the camera just in case someone else.
Professor, I have a small one message for you. I hope it will be good for us.
Okay, I see. When you make video for the web, I think there is some problem with audio system. If you are using microphone, this one is not working well to your wish. You will try to practice our speak. And the comment first, I thought it will not say the thing. No, you don't need to be super polite. Okay. I know how to fix volume, but it takes a lot of resources of my computer. If I post-process the recordings, I can enhance the sound quality. And if it is needed, I can try doing it tonight for this class. It's just it makes my laptop to work like for 4 hours to process 1 hour of video.
Yeah, I can understand.
If you need, I'm not telling anything new. Basically the same things, a little better, a little worse, were previous years, and they are on YouTube. You can find it.
Yeah.
And they are labeled the same way, like lab number 4, lecture number 7. You can browse and find them. Maybe.
Okay. It's already. It's fine. Okay. Thank you, Professor. Bye.
Yes.
So can you apply the example? I'm also assuming like this out this way.
Oh, just put one. Okay, it's very, very reasonable question. Yes. So I didn't do the following, but I'm sure if you put -1, the system will prompt to turn around. So basically, no matter what you start, it will self adjust and still come to the minimum when the order value. So this algorithm should give the same, almost the same answer, independent of this initial condition. But for now, we'll just use this one.
Sorry, and then is it possible value the parameter? Yesterday we used square.
Use square root of 2, it's just easier to do. Yes.